This object aroused interest largely following the discovery of its planetary system back in 2016, whose 3 components were spotted by transit method with the help of an automated 0.6-meter telescope in the European Southern Observatory, or the ESO, in Chile. The planets were initially dubbed TRAPPIST-1b, TRAPPIST-1c, and TRAPPIST-1d. However, further investigations revealed that the presumed location of TRAPPIST-1d was described incorrectly. Following that, 4 more Earth-like objects were discovered by astronomers with the help of the Spitzer Space Telescope. These were dubbed TRAPPIST-E, F, G and H. Thus, the total number of planets in the system reached 7, and on the 13th of April 2016, the parameters of these celestial objects were defined in more detail. All the 7 exoplanets are identical to our Earth in terms of their dimensions, with their radii ranging from 0.71 to 1.13 that of our planet. Planets B and C orbit their parent star in the periods of 1.51 and 2.42 days respectively. Initially, according to astrophysicists, both of these planets were comparable to Venus in all but exceptionally high temperatures. However, after their mass and density had been measured, it was TRAPPIST-1 that could be called Venus's analog. TRAPPIST-1b, the second closest planet to its star, is likely to contain a large amount of water and other volatile elements. The new data enabled scientists to find out more about the other discovered planets too. It takes TRAPPIST-1d 4.05 days to orbit its star. Its radius is 0.77 that of the Earth. The orbital period of TRAPPIST-1e is 6.1 days. Its radius is 0.92 that of the Earth. The orbital period of TRAPPIST-1f may last up to 9.2 Earth days. Its radius is 1.04 that of the Earth. The orbital period of TRAPPIST-1g is 12.3 days and its radius is 1.13 that of the Earth. Last but not least, TRAPPIST-1h is the 7th object and is the furthest from its star, with a rotation period of 18 days and a radius of 0.7 that of our planet. It should be mentioned that the initial estimates of the object's masses were likely to be rather conservative. Due to the analysis of the density of the first 6 planets, it was later ascertained that they contain a big amount of water and other volatile elements, which makes them considerably lighter than thought previously. As for the furthest of them, E, F, G and H, for all we know they may consist entirely of water. Only TRAPPIST-1c boasts a mass bigger than initially estimated, which may be indicative of over 50% of iron in its composition. Of the 7 planets known to be located in the TRAPPIST-1 system, 3 of them find themselves within the habitable zone, namely D, E and F. Speaking about the rest of them, following the estimates of its density, planet B is thought to contain either a small nucleus or else a considerable amount of volatile elements. Due to high temperatures of 127 and 69 degrees Celsius above zero on the surfaces of planets B and C respectively, water is not likely to remain in its liquid state there and is bound to float about as vapor. As for planets G and H, they are too remote from their central star to be potentially habitable. However, according to models suggested at Cornell University, the habitable zone of TRAPPIST-1 may well be wider, and allowing for volcanic hydrogen potentially acting as a greenhouse gas, there may be 4 planets within the habitable zone rather than 3. The density of TRAPPIST-1f is rather low too, and so it may well turn out to be an all-ocean planet. Here are the temperatures for all the planets in the system. The steady-state temperatures are given without including incident light dispersion and greenhouse effects. Just to compare, the steady-state temperature on our planet in the same conditions would measure 4 degrees above zero, and on Mars 47 degrees below zero. In November 2017, it was posited that the activity of the star didn't allow its planets to form and maintain their own atmosphere. It is accounted for by the fact that TRAPPIST-1 goes through periods of active flares, which may negatively affect the nearby celestial bodies, and thus render them uninhabitable for living organisms as we know them. Interestingly, the planets are located much closer to each other in comparison to our system's planets. The planet Mercury, which is the closest one to the Sun, is located 0.39 astronomical units from it, while the distance between TRAPPIST-1b and its parent star is just 0.01 astronomical units. As TRAPPIST-1 is a rather dim star, it is no easy matter to explore it. Red dwarfs like that are quite widespread across the universe, accounting for most of the galaxy's stellar matter. Plasma ejections on these stars are a rare occasion, although astronomers believe that there may be giant cold areas and compact hot areas with temperatures upwards of 4000 kelvins on the surface of TRAPPIST-1. If this conjecture proves to be true, scientists will proceed to confirm that the system's planets are constantly bombarded by powerful ultraviolet and X-ray radiation, which is able to destroy their atmospheres and render their surface completely sterile. The reason for that lies in the fact that none of the microorganisms known on the Earth are able to withstand intensive radiation emanating from flares of this kind, including the most radiation-resistant bacteria Deinococcus radiodurans. Nevertheless, in December 2017, atmosphere was proven to persist even in periods of high activity of stars, which implies that planets G and H may potentially have their own atmospheres. At the moment, astrophysicists' idea is to use more up-to-date telescopes for studying the matter. For example, the James Webb Space Telescope, whose launch is planned for March 2021. Today, the TRAPPIST system presents a great interest for the global scientific community, and even though it is highly unlikely that any advanced civilization will be discovered on its planets, we cannot ignore the fact that life forms in the universe may be extremely diverse and may differ from our perceptions of life as we know it, which implies that not all intelligent organisms are supposed to follow the scenario of our planet. If science manages to find out more details about this system in the nearest decades, many conjectures and doubts we have today about TRAPPIST-1 will most likely be cleared. Mankind has come across some extremely powerful radiation that reached us from deep space several times in the last 50 years. But as often is the case with space discoveries, the source was slow in being detected by astrophysicists. 1979. 3 US Vela satellites monitoring nuclear tests on the Earth detected an unusual gamma-ray flare. 1992. Astrophysicists assumed that there was a celestial object out there not known to science with a huge electromagnetic radiation coefficient. 1998. A gamma-ray flare in the constellation Aquila. A number of measuring devices registered an unaccountable anomaly with its source located tens of thousands of light-years away from us. 2004. All telescopes in the world were for a short time dazzled. Less than a second later, every cubic centimeter in the solar system experienced a wave of gamma-ray radiation. The most massive burst in the entire history of observations. And today we're closer than ever to finally putting our finger on the nature of this discovery. A magnetar is a neutron star with an exceptionally powerful magnetic field of about 10 to the power of 13 teslas, which in essence is trillions of times that of the electromagnetic radiation on the Earth. It is also one of the rarest and really most dangerous phenomena ever encountered by mankind. When a supermassive star is on the point of dying, a supernova occurs. Among the multiple scenarios of what may take place after that, only one may lead to the star becoming a magnetar after the supernova. Many of you would have heard about the Russian roulette at least once in your lives. According to the rules, only one cartridge is put in the revolver's cylinder. The chance of producing a shot after you have spun the cylinder is rather small. However, when it does happen, the consequences are truly mind-blowing. Be it as it may, Scientists are still at odds over what exactly this scenario would look like. According to the first theory, it's the inner energy of the star and its rotational energy that influence the formation of a magnetar. If a neutron star is formed at the time of fast rotation, the inner energy of this star, as well as its rotational energy, which is of great significance in the first several seconds, all create a powerful magnetic field. This process is known to science as a dynamo mechanism. But there is another theory as well. After the accretion process, the magnetar may be able to receive energy from another star. Scientists have discovered a magnetar which is on an escape trajectory from our galaxy. Most moving stars we know set off on their trajectories as a result of supernovae in binary systems. This means that the accretion process takes place between the two stars with a common mass center in a binary system. Matter from one star gradually flows to the other. In this case, this is the source of energy for a potential magnetar. Something similar happens with a basketball spinning around the edge of the basket. Sooner or later it is going to fall, but it's the spinning process that predefines the direction of the fall. Magnetars spin on their axes extremely fast, with a speed varying between tens and thousands of times per second. At the same time, their dimensions are record small. As a rule, the diameter of a magnetar reaches a measly 20 to 30 kilometers. Just to compare, the diameter of the Moon equals 3,474 kilometers. That is about 173 times that of the average magnetar. The mass, however, is a completely different matter. A magnetar with a diameter of 15 kilometers will be significantly heavier than our Sun, despite the dimensions. It is its staggeringly powerful density of the interior that is the reason for its high magnetic radiation. For instance, 1E1048.1-5937 is an anomalous X-ray pulsar located 9,000 light-years away in the constellation Carina.